Okay team, now we will see the characteristics of CAN. CAN has three basic characteristics. Let us see one by one. The first one is carrier sense multiple access with collision detection, CSMA bar CD. It is called like that. So what it means, every node, that means every node in the CAN network will monitor the CAN bus for the period of no activity. That means they will check whether there is no messages on the bus or there is no bus traffic. If that is so, all of them will get the equal opportunity to transmit. If that is the case, if two nodes get the equal opportunity to transmit the messages at the same time, if that is the case, they will use non-destructive arbitration method to decide which one is the winner. What is that? We will see them in detail in upcoming slide. As of now, you know that they use certain mechanism to find out a winner among the two nodes which has the equal opportunity to transmit. The next characteristics is the CAN uses message based communication. When you take RS-232, it is in byte, transmit 1 byte as one serial frame. Here it uses packets called as message and has been given a number. So the identifier, the given number, also called as identifier, is used to find out or used to determine the winner node among the two nodes which has the equal to transmit. How that will happen? We have a clear diagram in the upcoming slides. We will see there. One of the characteristic of CAN is it uses the messages for communication. The messages are named or identified with a number called as identifier. These numbers are used to arbitrate or to find the winner among the nodes which has the equality. If you have the lower value in the identifier, you will have a higher priority to transmit. For example, usually the power mode messages or engine status messages will have a very lowest number. For example, based on my experience, the power mode messages in automotive or automotive unit will have the message identifier with the number 80. So it is somehow the other messages like infotainment messages or the cluster status messages will have the higher number, which means that they are lower priority than this one. Are you able to follow me? Okay. Next step, each node uses one or more filter to compare the incoming messages to decide whether to take action on the message or not. So another characteristics is they use a filtering mechanism in each nodes, because the CAN bus will have a number of messages which are not applicable or which are not relevant to that particular node. So they use the filter as a gateway to resist unwanted messages which flows inside the node. So also has a certain feature, some messages which was transmitted by another node is not received by RX node properly. If that is the case, it is implemented in the standard itself, so it will re-request the messages. If there is a corruption happen in the bus after transmitting from the transmitting node, the receiving node, if it checks based on the checksum evaluation, if it finds there is a problem in the received message, it can request the other node to retransmit the messages. Okay, so that sort of characteristics the CAN has. There's no need to reconfigure the system when new node joins the system. So CAN has the flexibility of plug and play. That means all network nodes are connect a common can low bus terminated by 120 ohm resistor. So it is possible for a user to unplug a node and work with the remaining node without disturbing the system, without shutting down the system. He can work with the other node. By these are some of the flexibility that CAN has the CAN standard has for an end user. The third characteristics is error detection and fault confinement. So as I told you before, the CAN protocol requires each node to monitor the CAN bus to find out if the bus value and the transmitted bit value are identical. For example, it's a message is going out of a node. After transmitting the CAN message, the node will monitor the bus to check whether there is a problem happen in the bus. It is corrupted by other nodes or some other external factors using the checksum calculations. Okay, if there is an error happens, that is, it will take the necessary actions like retransmission of the messages, something like that. The CAN protocol requires the physical layer to use bit stuffing to avoid long sequence of identical bit value. So the standard also has some of the very good things like the bit stuffing. When there are sequence of 1, if that is the case, we need some sort of bit stuffing that's provided by the CAN standard. The defective nodes are switched off from the CAN bus. If some of the nodes which are present in the networks went to failure mode, those will be turned off from the network using the certain mechanism like bus off mode or sleep mode or something like that. So some of the error handling characteristics that exist in a CAN standard. When you implement these standards in a product or a chip, that will take care of all these activities by itself. CAN bus logic. Now we are in a position to understand how the CAN bus logic works. That means how the arbitration is done in the bus to find out the priority. For example, we have 3 nodes with 3 different identifiers. Okay, so what they are doing, they are simply doing AND operations over the bits of identifier. Here in this picture we have 3 nodes, node 1, node 2, node 3. All the table is marked with the D and R. The D means dominant, that means 0. R or 1 means recessive, that means 1. So when there is an high, it is called as recessive. When there is a 0, it is called as dominant. So when we AND 3 dominant, the result will be dominant. When there are 2 dominant and 1 recessive, the result will be dominant, because the ANDing or with the D will result D in the AND operations. So it is possible for the bus to become recessive only when all the nodes, the bits of identifier of all the nodes are recessive. If that is the case, the AND operation will produce recessive result. This is called as wired AND operation. Then the next step is, after doing the AND operations, how that arbitration logics works. Let us see here. All 3 nodes, node 1, node 2, node 3, has equal priority to transmit. Their identifiers, first bit of their identifier initially has a dominant, so the result, the bus result is dominant. Bus is in the dominant state. When all of them in the next pulse, next time interval, all of them becomes recessive. If that is the case, the bus also in recessive. Then node, all 3 nodes go to dominant state, so the result of the bus also in the dominant state. In the next time interval, in the next baud rate, what happens? Node 1 and 3 becomes dominant, but the 2 goes to recessive state. There it loses the arbitrations, so node 2 cannot transmit the messages. It is removed from the arbitrations. Only we have node 1 and 3 in the next baud interval, that is node 1 and 3 are in dominant, so the bus also in dominant, and the next sampling time it is becoming, that is node 3 moves to recessive, whereas the node 1 is in dominant. The result will become dominant because it is a wired AND, so bus is in the dominant state. So here the node 3 loses the arbitration, node 1 wins. So this is how the bus arbitration works in the CAN standard. It is purely based on the identifier that you have and the wired AND operation performed. This is a typical CAN node. So if you implement the CAN standard in a microcontroller, there used to be a CAN controller inside the chip, and there will be a TXT and RXT pin for CAN transmission. You have to employ a CAN transceiver for the buffering and to match the physical layer requirement. Then you will have a CAN high and CAN low pins. So the the CAN bus is a simple two-wire differential serial bus. The bus is terminated each side by 120 ohm resistor. This is very must. You have to use 120 ohm resistor to terminate the bus. So we have two states of CAN bus. What are the two different states? Usually in a digital world we have a zeros and ones. In CAN high, in CAN standard, to represent dominant or zero, there are different styles. The one among those is shown here. So when there is a zero, there is a CAN high is represented in the red line and CAN low is represented in the green line. So it goes to the CAN high go to recessive and low goes to dominant. So both of them in totally they represent the zero. Then both of them comes to, that is high comes to low, dominant, and low goes to recessive. If that is the case, it becomes 1. So this is a style in which we represent zeros and 1 in the CAN standard. This is the final bus logic waveform. This is how the CAN bus will look like. The CAN bus state will look like when we transmit these particular bits over the bus. This is another style in which you can transmit the CAN packets over the physical layer. You will see these sort of waveforms in the physical layers. If you connect with the DSO or an CRO, you can able to see these waveforms in the oscilloscopes. The next topic will be the types of CAN frame. We will see them in detail. Thanks.